Right, in this video, we're going to look at systems of linear inequalities. Now, what that means is just like when we had systems of equations, we had more than one equation that we had to satisfy. When we have systems of linear inequalities, that just means we have more than one inequality that our solutions have to satisfy. Okay, so it's a very similar concept to something that we're used to. So the directions would be represent the solution each system of linear inequalities on a graph. So again, this is a system of linear inequalities. We're given two inequalities that all of our points have to satisfy. Y has to be greater than 2x minus 1, and at the same time be less than or equal to negative 3x plus 4. So this is really a similar process, just a way of squeezing two, like squeezing two graphing inequality problems into one. Okay, we want to graph each of our inequalities and figure out which specific section makes both of these inequalities true. So the first thing we need to do here is just graph both boundary lines. Okay, now we just have two boundary lines that we need to break our graph into, or break our graph up with. So again, we're good at graphing lines at this point. We want to know when will y equal 2x minus 1, so our y-intercept, negative 1, and our slope is 2. Okay, so we start at negative 1 and we just move with our slope, which means we go up 2 over 1, up 2 over 1. Now, because we practiced already, we're good at understanding the difference between a solid line and a dashed line. This is dashed, right? Because this is just greater than, not greater than or equal to. So this boundary line is where y equals 2x minus 1. Okay, so this breaks it up into two. So we want to know which half of the graph is y going to be greater than 2x minus 1. Now we have the other boundary line. Y is less than or equal to negative 3x plus 4. So y-intercept, positive 4, and our slope is negative 3. What does that mean? Well, we just go down 3 and over 1, down 3 over 1. Okay, solid or dashed? Solid. And as you can see, we just have our two boundary lines. Now there's a few different ways of going about doing this, and I want you to discover kind of the best way that works for you. I'm going to show you one way that relates to what we did before, because I think that's the way that's most applicable and can transfer to different problem sets. But you need to understand why we're doing what we're doing, okay, why we're testing the points. And you also need to understand how the solution relates to the inequalities. Okay, how does that point relate to these inequalities and their inequality symbols? And then once you start realizing and paying attention to what we're doing, when do points work, when do points not work, what does it mean in terms of our inequalities, you're going to start to discover your own shortcuts and your own better guesses and better choices for picking points. Okay, and that's on you. So you need to listen to how we do it and then think through on your own why we're doing it this way. Why does it work? Why doesn't it work? And as again, once you start doing that, you're going to discover how to do it a lot quicker. So, as you can see, we want to find when will y be greater than 2x minus 1. Okay, so here's our line where y equals 2x minus 1. So we want to know on which side of that line is it going to be greater. And at the same time, when will this y also be less than negative 3x plus 4? So here is it when it equals negative 3x plus 4. So we want to know on this which side of this line is y going to be less than negative 3x plus 4. So again, until you discover your own shortcuts, we have 4 different regions to check. We want to know, are the points, the solutions overlap here? Are the solutions in this region that make them both true? Are the solutions in this region that make them both true? Or are the solutions in this region that make them both true? So again, the second thing we do is we test points. Okay, but now we have 4 regions, not just 2, like we did before. So we want to find when will y be greater than 2x minus 1. Okay, so let's pick this point. And when will this be the same time? Is this the same time when y is going to be less than negative 3x plus 4? So let's pick a point here. Okay, this is the point 1, 4. So we want to know, is 1, 4 a solution to both of these inequalities? So again, this is what we think in our mind. Is 1, 4 a solution to both inequalities? Okay, so let's check. Our x is 1, so we do 2 times 1 is 2, minus 1 is 1. Our y is 4, so is 4 greater than 1? Yes. Okay, so far so good. 1, 4 is a solution to the first inequality. But is it also a solution to the second inequality? So we test it the same way. Negative 3 times 1 is negative 3, plus 4 is positive 1. Our y is 4, so is 4 less than positive 1? No. Okay, so this point isn't a solution. Okay, it made our first inequality true, but it didn't make our second inequality true. Now again, what we want to do now is understand that, well, because this made our first inequality true, this half of the graph is where y is greater than 2x plus 1. So we're going to pick a point still on the same side as this line, or just pick a point in another region. Again, we just want to find which one of these 4 regions make both inequalities true. So we want to stay on the same side as the point 1, 4 of our line y equals 2x minus 1. So let's check over here. Okay, so is the point negative 2, 3 a solution? And we do it the same way. This is why I'm not writing stuff out on this side, because we've got a lot of practice doing this, and this should be done mentally. So x is negative 2, so 2 times negative 2 is negative 4, minus 1 is negative 5. Okay, y is 3, so is 3 greater than negative 5? Of course. Now let's check our second inequality. So again, this makes the first one true, which is what we expected, because it's on the same side of our line 2x minus 1 as the point 1, 4 is. So now let's check our other inequality. Negative 3 times negative 2 is 6. 6 plus 4 is 10. Okay, our y again is 3. So is 3 less than 10? Yes. So what does this mean? Well, this means the point negative 2, 3 makes both of these inequalities true. So that means every single point in this region, which is split up and created by these two intersecting lines, is or are all of the solutions. So every single point over here is a solution to both inequalities. Okay, so this is the side of the line where y is greater than 2x minus 1, and then this is the side of the line where y is less than negative 3x plus 4, and this quadrant, or this section, or region, is where those two solution sets overlap. So this is the points, these are the solutions that make both of these inequalities true. Okay, so why don't you try these two? And again, our steps. We graph both of our boundary lines, just like we did before. Then we're given 4 different regions to check points in. But you need to be paying attention to the points that you pick. And what if they make one of them true but not the other one? And what would be a good guess, or what would be a good region for your next point? These are things that you have to pay attention to so you can discover a quicker and more reliable process. Well, not more reliable, but just quicker and smarter process. Okay, so press pause, try these two, then press play when you're ready to check. Okay, our first system, y is greater than or equal to negative x plus 4, and y is greater than x minus 4. So let's graph both of our boundary lines. Negative x plus 4, the y-intercept is 4. The slope is negative 1, so that means you go down 1 over 1, down 1 over 1. Okay, solid or dashed line. Good, solid, because it's or equals 2. So this is where y equals negative x plus 4. Our next boundary line, y is greater than x minus 4. So this time our y-intercept is negative 4, and our slope is 1. So we go up 1 over 1. Now is this line solid or dashed? Good, dashed. Okay, as you can see, we have 4 regions. So we want to find when will y be greater than negative x plus 4, and at the same time be greater than x minus 4. Okay, if you did your work correctly, you would have found that it's this region up here. Okay, and I'll just verify one of the solutions with you. So let's try the point 4, 2. So x is 4, so negative 4 plus 4 is 0. Is 2 greater than 0? Of course. So 4, 2 is a solution to our first inequality. Is it also a solution to the second one? 4 minus 4 is 0. 2 is greater than 0. So 4, 2 makes both of these inequalities true. So the region that contains 4, 2 is the solution to, or the solution set to both of these two, or this system of linear inequalities. Okay, this next example. Okay, so we have to graph these boundary lines. So the first thing we have to do for this first one is we have to solve for y. So 4x minus 5y equals 5. So negative 5y equals negative 4x plus 5. So y equals 4/5 x minus 1. Okay, we need to get it into slope-intercept form. So our slope is 4/5 and our y-intercept is negative 1. So we start at negative 1, slope is 4/5. Okay, so up 4 over 5. Solid or dashed? Dashed. Okay, our next boundary line, y equals 2x, so our y-intercept is 0, and our slope is 2. Okay, solid or dashed? Solid, because it's or equals 2. And we do our best to hit our points. Okay, so we want to find which section of this graph will make 4x minus 5y less than 5, and at the same time y be greater than 2x, and that's this region. And you figure that out by testing points in each of these until you find the ones that make both true. So I'll just show you to verify. Let's try the point negative 2, negative 1. So 4 times negative 2 is negative 8. 5 times negative 1 is negative 5. Negative 8 minus negative 5 is negative 3. Negative 3 is less than 5. So good. The point negative 2, negative 1 makes our first inequality true. Again, you're just substituting negative 2 in for x and negative 1 in for y and seeing does this expression less than 5? It is. We check our next point. X is negative 2, so 2 times negative 2 is negative 4. Y is negative 1. Is negative 1 greater than negative 4? I mean, of course it is. So this point is a solution, which means every single point in this region was also a solution. Okay, so this is very similar to what we did before when we were just graphing linear inequalities. Now we just have two. We want to find which region of the graph are the points that make both of our inequalities true. And you do that by just checking points in each region until you find the one set that makes both inequalities true. Okay, now there's just two special types of examples. Now they're the exact same thing, but I just want to highlight kind of the special lines that go into these and make sure we're not afraid or scared of some of the boundary line equations. Okay, so we'll start with the one on the left. Again, don't press pause and try these on your own. We'll just start the problem together. So we have, again, this is a system of inequalities. We have x is greater than or equal to 1 and y is less than 1/2 x. So we need to graph our boundary lines. Now, this first one might not be something that we're so comfortable with, but really this line is very easy, or this boundary line is going to be very easy to graph. So we want to know, when will x be greater than 1? So we start with, well, when does x equal 1? Well, x equals 1 here. Okay, so when we have an equation or an inequality and we give it a boundary line, we want to graph the line x equals 1. That's the boundary line we want to graph. When will x equal 1? Well, that's here. Well, since x equals 1 and we have nothing else in that equation, that means x always equals 1. So our boundary line in this case is simply the vertical line at x equals 1. If we had x is greater than 4, we'd have a boundary line at x equals 4, and that'd be a vertical line at 4. If x is greater than -5, we had a vertical line at -5. So it's very easy. Whenever it just gives you an x, it means x is always 1 for the boundary line. So here x equals 1, so x is always 1. All these points on this vertical line have an x coordinate of 1. And that's what the boundary line is. It's actually very simple. Now it's solid again because this is or equals to. Okay, now we just need to graph this other boundary line. Y is less than 1/2 x. So y-intercept in this case, now we have x's and y's, so we have a typical line with the slope and a y-intercept. So our y-intercept is good, 0, and our slope is good, 1/2. And what does that mean? Well, we go up 1 over 2, up 1 over 2. Okay, now solid or dashed. I mean, this one's dashed because it's not or equals to. And now it turns in the same problem. So why don't you finish this one up on your own? Okay, figure out which points give us that x is greater than 1 and y is less than 1/2 x. So press pause, try and find the region, then press play when you're ready to see where it is. Okay, good. This is the region. Okay, now the nice things about these inequalities are they're a little bit more intuitive. Well, x needs to be greater than 1, so obviously you need to be greater than 1. These are the numbers where x is greater than 1. So again, once you pay attention to what you're doing, these seemingly challenging system actually becomes a little bit easier. We need x to be greater than 1. That's obviously to the right of our line x equals 1, so that's when it equals 1, and we could obviously see that these numbers are bigger than 1. And y is less than 1/2 x is a region down here underneath. So this is where they both overlap. Okay, let's look at this next one on the right. We have y is greater than -3/2 x plus 3, and y is less than -1. Okay, so this first one, this first boundary line, is a little bit simpler. We're used to it at least, not really that it's simpler. We have a slope and a y-intercept. Our y-intercept is good, 3, and our slope is right, -3/2. So we go down 3 over 2, down 3 over 2. Okay, solid or dashed? Right, dashed because it's not or equals to. Now we have just the line y is less than -1. Okay, again, this might be something we're not so familiar with, but this line's actually very easy. Okay, this boundary line y equals -1 is actually very easy to graph. Okay, so over here when we had x is greater than 1, so we graphed the boundary line x equals 1, and that's when all the x coordinates had to be 1. So we had a vertical line at 1. Now we're saying, where's the boundary line y equals -1? Well, y equals -1 is right here, and if we want y to always be -1, which is what this boundary line is saying, well, that's just a horizontal line at -1. Okay, so the boundary line's at -1, and it's dashed because this is just less than. So whenever you're graphing lines where it's just y equals a number, that's just a horizontal line because y always has to be that number. So if we had y is less than 5, we'd graph the boundary line at y equals 5, and that'd be a horizontal line at 5. Y is less than 2 would be a horizontal boundary line at y equals 2. Because here at y equals -1, our y coordinate is always -1, and that's what that means. So again, this is just a very easy, it's actually a much easier line to graph. We just have to get used to seeing it. So again, this is more intuitive. We want y to be less than -1. It should give you a hint about what points to pick and where to pick your good points to find the region that makes it true. So press pause, try and find it, and press play when you're ready to see where it is and if you did it correct. Okay, so again, we want y to be less than -1, so that's obviously the numbers underneath that line because the numbers decrease as you go down. And we want y to be greater than -3/x plus 3, so that gives us the region over here. Okay, good. So our process for doing these was we graph both of our boundary lines, and we have 4 regions to check for the solutions. And the solutions have to be the points that make both of these inequalities true. If you have more than one inequality, you have to find ones that make them both true. And you need to pay attention to what you're doing and good points to pick, okay, and how those solutions relate to the original inequality so you could get better and discover shortcuts and pick better points and think through it more intuitively. And you become much better at this, and that comes with practice. So if you need more practice problems, refer to some of the other online resources or the packet or the textbook.